Hey kiddos, happy lesson number 7. It was really neat to see a lot of you at the sign pickup on Saturday. That made me very happy. So let's get going with lesson number 7. Today we're talking about nuclear processes. We're going to debrief the simulation that you completed for homework. And then we're going to define the relationships of nuclear decay. So we're going to talk about how we can represent nuclear decay using equations, and then we'll talk about gamma decay in terms of nuclear energy levels, and then I will leave you with an activity that you will use to model nuclear decay and half-life. It might involve pennies or M&Ms or Skittles, whatever it is that you have at home that has two distinct sides and are all identical. All right. Okay, so the nuclear processes simulation, hopefully you saw that there were 4 types of decay. There is alpha decay. Again, if you remember, it's typically just written as the Greek letter alpha. Negative beta decay, right? Sometimes written like this. Positive beta decay, sometimes written like this. And then gamma decay. And there should have been some patterns that you noticed as those decays were happening. So let's first talk about alpha decay. So that alpha decay, if you remember, is the decay that happens when you are emitting an alpha particle, which is a helium nucleus. Okay, and you probably noticed that there was a parent nucleus that decayed into, so this is an official symbol in this sort of equation, decayed into a daughter nucleus plus an alpha particle. Okay, so what's a specific example of this? Well, radium often emits alpha particles. So radium has a mass number of 226 and an atomic number of 88. It decays into an alpha particle. You can write it like this, alpha 42, or helium 42. Either one of those is acceptable. Plus, now what does this have to be? Okay, we're conserving the number of nucleons in these equations. So if you started out with 226 nucleons, right, and decayed into something that had 4, then that means the number of nucleons that are left over have to help define what material the daughter nucleus is. So 226 minus 4, that must be 222 nucleons. We started out with 88 protons. An alpha particle has 2, so this must have 86. Okay, and this particular nucleus is called radon. Okay, so we're conserving nucleons. Whatever we have before the decay has to be the total of what we have after the decay. Okay, and so what you're noticing in alpha decay, there's just a daughter nucleus and an alpha particle. The alpha particle is the only thing that's emitted in alpha decay. Okay, and here's a little bit of guidance here. So we're using generic abbreviations for the parent nucleus is being abbreviated as X, and the daughter nucleus is being abbreviated as Y. And so if you take the mass number and the atomic number of the parent, subtract 4 from the atomic number, subtract 2 from the mass number because of this alpha particle, you'll get the atomic and mass numbers for the daughter radius, or sorry, for the daughter nucleus. Okay, so some important things to note about alpha decay is that about 30,000 ion pairs are generated per centimeter of travel. So alpha particles are pretty high ionizers in the air. Remember, it's that ionizing radiation that we're concerned with in terms of like causing cancer and stuff like that. All right. However, alpha particles are big, right? And they're not very penetrative, so they can be shielded by skin. They have one single energy, right? Their energy is quantized, which is interesting. And they are directly ionizing. They hit air particles, other atoms or molecules, and can ionize them directly. And really, they don't travel very far. They have a 1/2 inch range in air, but they're pretty high energy. So they're big, they don't travel very far, but they pack a punch. All right. Here are a couple examples. All of these atoms down here produce ionizing radiation. They're not a super external hazard because they can be stopped by skin, but you don't want these high energy big particles inside your body. That would be pretty damaging. All right. Okay, so let's take a look at this energy and alpha decay. This is sometimes a graphic that you will see when talking about alpha decays. So if you are, so you've got kinetic energy of all of the alpha particles that are within an atom. And there's a certain amount of energy required to penetrate that barrier, then they won't be able to penetrate. So you can take an alpha particle, if it's excited, up above this energy level, then it will be able to get through this barrier. And this is a classical mechanics view of alpha decay. Right, if an alpha particle has enough energy, kinetic energy, to get up above this point, the alpha particle will get released, just kind of like with the photoelectric effect, and you'll see that alpha decay. However, there's this idea called quantum tunneling, right, where it says that a wave function in a potential well, just like an electron has a potential well within an atom we talked about with the photoelectric effect. We can treat an alpha particle like a wave, right? That also has a wavelength and a wave function from the Schrodinger equation, right? A probability that it will exist in a certain state. A wave function in a potential energy well has large kinetic energy and momentum, but a short wavelength. Okay, and then outside of the potential well, outside the nucleus, it has less momentum and a longer wavelength. And this is really hard to conceptualize, but I will ask some questions. I'll point you in the direction of a couple of questions related to this idea in the textbook, so you can kind of see how this is used in problem solving.